Okay, everyone, so today we're going to be looking at the naming of chemicals and how to write the proper chemical formula for various molecules and compounds. Okay, so a lot of this is going to be repetitive, so it will be a review of what you've already learned from grade 9 and 10. There may be a few new things. But obviously we'll spend, this is kind of a multiple part lesson because there are of course many different types of compounds. So we are going to have to go through each of them since there are different naming rules for each one. And we'll also go through on how to do the formulas as well. So first we're going to start off with ionic compounds. So the part of the difficulty when you're naming things has to do with looking at the type of compound that it is. So we have a metal and a non-metal. We know we have an ionic compound. So just to review, remember metals are on the left side of the periodic table, of the staircase, I should say. The non-metals are found on the right-hand side of the staircase on the periodic table. Now keep in mind, hydrogen is also considered to be a non-metal. However, you're going to see, so remember I mentioned already a few times that there are exceptions to every rule when we're looking at chemistry. Technically, ionic compounds are compounds that are composed of ions. So meaning you have a positive ion and a negative ion that are coming together to create a structure. So for example, potassium iodide. So potassium is a positive. Since it's a metal, it will lose electrons. And iodine is a negative when it gains an electron. So when you're naming ionic compounds, what you do is you write the full name of the metal. The metal name never changes. And the non-metal will actually end with the suffix IDE. So potassium does not change, but iodine becomes iodide, okay? So hydrogen and sulfur, you're probably wondering, well, those are two non-metals, okay? But however, hydrogen, when it becomes an ion, is positively charged. Sulfur, when it becomes an ion, is negatively charged. Actually, it's -2. So technically, you have a cation. Remember, positive ions are referred to as cations. And negative ions are anions. So this would actually be called hydrogen sulfide. Okay, so pause the video, give these next two a try. So we have magnesium and phosphorus and lithium with oxide. Okay, so magnesium, remember the name of the metal does not change. Phosphorus actually becomes phosphide, okay? And then, just so I have more room here, lithium and oxygen becomes lithium oxide, okay? So typically naming ionic compounds is pretty straightforward. You name the metal, you change the ending of the non-metal to the IDE. Now, how do you write the formula for an ionic compound? This is where it comes into play, where you have to understand what the charges are of the ions you are creating with this structure. So just to quickly go over this, I have the periodic table here. Remember that the charge of the ion essentially is dependent on the number of valence electrons that something has. So everything in group 1 will have 1 valence electron. Group 2 has 2 valence electrons. And if you recall, or maybe you haven't recalled this, but anyways, the transition metals that are in this center block here, they kind of don't really follow a specific trend. So here we have group 1 has 1 valence electron, group 2 has 2. This center block, we're going to kind of skip over for now. So it's like 1, 2, we're going to skip over a few. Group 13 has 3 valence electrons. 14 has 4, 5, 6, 7, and of course our noble gases all have 8, except for helium, which has only 2. So what does this have to do with anything? Well, remember that the goal of creating an ionic compound is to achieve a stable octet. So meaning, if I have oxygen that has 6 valence electrons, I know that oxygen is going to want to gain 2 more additional electrons in order to reach its stable octet. So the charge on oxygen would be a -2. Keep in mind that non-metals will always be a negative charge, unless, of course, we're talking about hydrogen, because hydrogen is going to become a +1. So remember that the number of valence electrons impacts this here. So magnesium has 2 valence electrons. It's in group number 2. So in order to become stable, it will lose those 2 electrons. So metals will lose electrons, non-metals will tend to gain. So once you've established what the charge is, what we would then do is something called the crisscross rule. So what that means is the charge that is on the metal, so in this case we're doing lithium on oxygen, the +1 on lithium, because it's in group number 1, would cross down to the oxygen's subscript side. But remember, we never write in the number 1. Just by having the element symbol there, that represents that there is 1 atom of that particular element. The -2 that's on oxygen, because it's going to gain 2 from its 6 valence electrons, will crisscross down and become a subscript next to lithium. Okay, so a couple of things. When you're writing out your symbols, the positive ion will be written first. So meaning the metal, or the positive ion, will always come before the negative ion. When you're bringing down the numbers, you never bring down the number 1. You never write that down. And of course, you never write in little positive and negative symbols. The positive and negative is just there to represent the charge. What we care about is the number. Okay? And last but not least, if you are able to reduce the subscripts, you will always want to have the lowest numbers represented. Okay? So actually, I'll do this first example with you, and you'll see what I mean with that. So here we have aluminum and phosphide. So remember, the "ide" has been changed, so this is phosphorus. Let's take a look at the periodic table. So aluminum is in group 13, which means it went 1, 2, we skipped over a few, and this is now 3. So there are 3 valence electrons in aluminum. So the charge here would be a +3. Now phosphorus, if we take a look at phosphorus, phosphorus is in group number 15. It has 5 valence electrons, which means it will have to gain 3. It's a non-metal, so it's gaining. Gain 3 in order to have its stable octet. So when we're writing our charge here, this would be a -3. So crisscrossing this will essentially bring the 3 from phosphorus down to the aluminum. Remember, we don't write in the negative. And the 3 from aluminum would come down where the phosphorus is. Remember, we do not write in the positive. But this is an example where we are able to reduce the subscripts. So 3 and 3 has a common, can be divided both by the same value of 3. Right, so we can divide 3 by 3 and 3 by 3. So what that means essentially is that aluminum phosphide, instead of being Al3P3, would just simply become ALP. So remember, we don't write in the number 1. So it's like we're saying 1 aluminum and 1 phosphorus. What we care about here is actually the ratio of elements. So 3 to 3 is the same thing as saying 1 and 1. Okay, so kind of just as a side note to give you a completely something different here. Let's say we had 2 elements and the subscripts were 2 and 4, right? We would not keep that as the final formula. You would reduce that down. So here, the common multiple would be 2. So we would say X and then Y, 2. So the ratio was 2 to 4, and now we have 1 to 2, which is exactly the same. You always want to represent it in the lowest possible value. Okay, so pause the video, give these 3 a try. Make sure you have your periodic table handy, of course. So we have barium nitride, potassium sulfide, and calcium oxide. Okay, so barium nitride. So we have barium and nitrogen. Barium is in group number 2, so it has 2 valence electrons to lose. Nitrogen is actually in the same chemical family as phosphorus, so it also has 3 it needs to gain. So the 3 would come down near barium. The N would have a subscript of 2 from the original barium. Oop, oh my goodness, I'm saying something and I'm doing the other opposite. So let's go back here. So the barium would be 3, nitrogen would have the 2. So Ba3N2. This cannot be reduced any further, so this is your final formula. Potassium and sulfur. Potassium has a positive 1. It's in group number 1. Sulfur has negative 2 since it has 6 valence electrons. So when we crisscross this, you should have K2 and S with no number written in because it's essentially a 1. Calcium oxide. Calcium is positive 2. It's in group 2. Oxygen is in the same chemical family as sulfur. So this is an example where we have another possible reduction. So Ca2O2 would then just become CaO. Now, when you are doing this, you do not have to show your work here. So you know how I'm showing the crisscrossing and I'm showing how I'm reducing it? You do not need to do that. I'm just going through this so you understand where I'm getting these numbers from. So technically, when I'm asking for the formula for calcium oxide, you can jump directly to just CaO. So once you get more and more comfortable with doing this and how to read the periodic table and understanding the charges, you will eventually get to the point where you don't have to do this. Some of you may already be there. Some of you may have to write them out and do the crisscross, and that's perfectly fine. So transition metals. So transition metals are those ones that we skipped over when we did our rules of, group 1, group 2, and then we skipped over a few. So transition metals are those ones that are in the center block. So let me go to our periodic table for a second. So they're the ones that are basically from group 3 all the way till group 12, right? So they're kind of this center section here. I have to admit it also includes some of these elements that are down here, these heavier metals like tin and lead, thallium, but you'll get more comfortable with knowing transition metals as we go through this. So transition metals essentially can create sometimes more than one type of ion. Now, for example, copper can have copper positive 1 or copper positive 2. So they're known as what's called multivalent. So meaning there are some copper elements, I should say atoms, that have 1 valence electron. My circle is not great there. One valence electron. But then there are other coppers that have 2 valence electrons. Okay? So what happens there is if you're making a compound with copper positive 1, that's going to have a different structure than if you were creating it with copper positive 2. So it's important that when you are doing the crisscross rule, you have to make sure you are using the correct ion, right? So here, the crisscross rule with positive 1 is going to be 1 and 1 with chlorine. However, if you have copper positive 2, when you crisscross with chlorine, you have a subscript of 2. So you're probably wondering, well, how do you know which one you have? Okay, well, it depends on, of course, the structure you are looking at or the name. Just so you know, when you are looking at your periodic table, there is a way that you can, let's see if I can zoom in a little bit more. Okay, so this isn't great. You can probably see it better on your scan, or I should say the one that you have even in your textbook. You can see it better. Let me see if we can use, so the one from your textbook is right here. It's just small. Let's do that. Okay, so the one in your textbook is actually pretty nice. It does not show you all the possibilities, which is why I don't really use it. But for now, especially when you're doing practice with Roman numerals, transition metals, it may be easier for you to use your periodic table from your textbook.